Again, if I'm asking for full complexity analysis, that's what I'm asking for. All right?
So that's in the next lab?
Yes, on the next lab, when I ask for full complexity analysis, that's what I'm asking for. All right. My one note that I kind of skipped over here, important note, n squared is the highest or largest term. Just keep that in the back of your mind for now. Hopefully you can see that if you try to do analysis of any type of complex algorithm, it will start becoming a nightmare very quickly. This is why Big O came about, and Big O is going to simplify this problem immensely for you. So we measure an algorithm's time requirement as a function of the problem size. So we were talking about the size of the, n, the size of the array, and then how long does it take time-wise. It may depend on different parts of the application. Some application will run fast on a small or a set, others will require slow. For example, let's say problem size was n, algorithm A requires 5 times n squared time units to solve the problem, size n, but B only will require 7 times n. So the algorithm's proportional time required is known as its growth rate, and we can compare the efficiency by comparing their growth rates. So notice that these numbers, as n increases, are going to grow at a different rate, or the amount of time they consume is different. So the question is, which of these is better? Ooh. Which one of these is better? Which one of these is faster?
The first question.
Why?
It's not exponential.
It's not exponential. Did I do big O in OOP? No? Okay, great. Well, that was a slightly trick question. Because in reality, as long as n is under, 7 or less, the second one's faster. But then after that, there's no comparison.
Yeah.
So, but do you usually care about the small numbers?
No.
Not really. So, the real answer, which is better, definitely the first one. Because we don't care about the small stuff, so to speak. This is to show you dominating terms. What happened here? So here's the full formula, and this is just that one term 4 times 3 to the end. And percent of total, notice this one's 1237, so it's only 32% of the total. But as the number increases, hopefully you can see that the dominating term is by far the exponential, more than these. These become, as this increases, the rest of this is really just superfluous. This implies we really only care about the dominating or the highest term. We really don't care about the rest of it, or at least for large n. Here's another example. Log base 2 of n of 10, 3, 106, 1009, 10,013, and 100,016. Yeah, log base 2 of n is actually a really good algorithm. If you could write those all the time, that'd be great, guys. Keep that in your mind. And, of course, it's linear, so it's just going to match. N times n log n is actually still fairly decent. N squared, you start getting a little big. So notice that I'm using exponents here because numbers are starting to get too big. N cubed is definitely worse. And then 2 to the end, give up. Just give up. Just no. In actuality, when you have something that's exponential, like 2 to the n or 3 to the n, we usually call that problem intractable. It will not be done. Given any input, like even 100, 10 to the 30th, it's not going to happen in your lifetime. Basically, ordering. Hopefully you can see there's an ordering here. If your program takes O of 1, that's awesome. But probably anything's going to take longer. So you have log n, which is slower, then n, which is slower, n log n is slower, n squared is even slower, n cubed is even slower, and then of course 2 to the n, 3 to the n are even slower as well.
Is there ever a situation where there's a program that would be 3 to the?
Yes.
Have you made one?
Oh yeah.
Oh yeah.
Oh, I've made ones that are way worse.
Oh man.
You do it on purpose?
So far.
Okay, all right. Maybe one time you just messed up.
Well, you know what? I take that back. I think I did a couple of times make one that went, ooh, yeah, that was bad. Well, you're solving a complex problem. You're just trying to get code that works. You're like, oh, good, it works for 2 elements, 3 elements, 4 elements. Let me type in 5. Oh man. Yeah, that's how you know it's exponential. When 2, 3, 4, no problem, and then you just increase it by 1, and then it's game over. Dead on. So what is big O? Big O is we're only going to care about the largest term. We're not even going to care about the factor in front of it. So it's called the growth rate function. Since capital O is used in notation, this is usually called big O notation. The algorithm is n squared. This should be 2 to the n over here, not n times 2. If it's n squared, we call it big O of n squared. If it's proportional to n, it's big O of n. All right, proportional. In other words, we have n squared minus 3n plus 10 seconds to solve. If you want to be all mathy, you can say if constants k and no exist such that the whole k times n squared plus no is greater than the actual formula for all n and no, then the algorithm's order n. In fact, k is 3 and no is 2 in this situation. So we just call that the algorithm requires no more than k times n time units, or we just say it's O n squared. An easier way to do this, let's go look at this function. What's the biggest term? Hey, n squared. Okay, we'll just shove it over there. So there's the math way to do it, which is the correct way, or you can just do it like everyone else does. Here's some good examples. 50 times n squared plus 31 n cubed plus 24 n plus 15 is just no of n cubed. Hey, look, we just took this n cubed and put it over there. Yeah, it's the game spot the highest term. 3 to the n, oh, it's that guy. This can be tricky. Why is this bottom one n cubed? Right. Remember to multiply it out first. You got to multiply it out and get to the terms. Second one's n log n, because n times n log n is slower than 10n for large n. All right. Everyone good with this? Think you could spot it out? Got this? Yeah.
3's the largest.
What?
Constant's the largest.
All right, let me explain what these functions are, because you'll probably be seeing, especially these a lot. O of 1, time requirement is constant and independent of program size, aka it takes this amount of time whether it ends in million or 2. That is a great algorithm, but very few actually can achieve that efficiency. Log n, time requirement for a logarithmic algorithm increases slowly, very slowly, as the problem size increases. This is actually, you know how exponential, give up all hope? This increases, inversely to exponential. That's why log n is so nice, because you can keep tacking on numbers and it's really not going to slow down that much. So log n, very nice. O of n, sometimes you just have to go linear. Time requirement for a linear algorithm increases directly proportional to the problem size. So you add, you multiply it by 10, your problem size, you add another base digit to your problem size, that'll probably take about 10 times as long to complete, or some proportional there. In log n, it is more rapid than linear, although not by much, because multiplying by log n doesn't add that much complexity. It does add some, but it's definitely far superior to n squared, where requirements quadratic algorithm, it increases actually very rapidly. Although with good computers, with the computers we have nowadays, you can still solve that problem fairly quickly. In general, you don't want to do n squared unless you have no other choice, but do keep in mind that n squared will eventually complete, definitely within your lifetime. And same thing with n cubed, it's going to be slower than n squared, but again, it'll eventually solve. To the n, the time requirement is too rapid to be practical. When I say it's not going to complete in your lifetime, I'm not joking. It literally will not complete in your lifetime. I'm not exaggerating.
Even with the supercomputer?
No. Now, there's certain things quantum computers may actually solve for this case. But right now, with our conventional machines, it's not going to happen.
Has anyone just put it in just to see how long it takes, just to let it go?
Let it go? No. I mean, what are you going to, the power to your building is going to run out. After a year, you're going to have a fault and your machine's going to stop. So we could have a generator, keep it going, but it's not worth it. It's just not worth it. And most of the time with algorithms that are like this, we'll do approximation so that it turns into an n squared. And then we'll say it's within 50% of the correct answer. And most of the time that is acceptable. And then there's also some programs that you just can't write. Okay, let's do some practice. What's the big O of this? O of n, yep. C3 plus C4 plus C5 times n plus some constant, so it's A times n plus B. It's O of n. How about this guy? Yep, n squared. Blah, 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 blah. Basically, you have an n right in here, and you're running it n times n squared. All right. How about this one? N cubed? Let's see, is that actually correct? Yeah, that one's going to be correct. Notice I just started estimating when I did my full analysis, aka I'm tired of this. You do not need to know the exact number of iterations to find the big O. All right, it's n cubed. It's slower than the other two. Significantly slower, actually. All right, here we go. How about this guy? Woo-wee. I like my first statement. Constants are virtually superfluous when working with big O. Yeah.
How much is a function called again? It's just one.
Yeah, it's one. All right. Someone read the slides. Because I'm kind of. You have to solve the recurrence relation. You'll learn how to do this in discrete structures. Anyone taking discrete right now? Has anyone taken discrete before this course? You took discrete?
Yeah.
Okay. Did you do Towers of Hanoi?
Hanoi?
Hanoi? The discs that you had to move from one peg to another?
Did that in Alice.
You did Alice.
Yeah.
All
I think
right.
I may be talking about different discrete math. I'm talking about discrete math.
Yeah, discrete. Oh, structures is what we call it. Or did we call it discrete math? I forget which one it's called.
It's math 330, discrete math.
Yeah. So you solve recurrence relations to find the final formula. I'm not going to go into it, but you use that to solve this. So when we make you take 330 and you're thinking, how can this ever possibly be useful? Here it is. To find the big O. Huh?
The one time.
No. Every time you need to do a big O analysis of a recursive function, boom. It's right there. And in actuality, another course you should take, won't be offered next semester, but after that is called competitive programming, which you'll be able to quickly do analysis of different algorithms you come up with to figure out what is the best one to use to solve a problem.
Hey, is it true that on HackerRank you're in like the top 1,000?
I doubt it, but I could be. I haven't checked in a while.
Were you ever towards the top?
In certain categories, definitely. The thing about it is I didn't have time to do it over the summer, so they probably released more problems that I haven't solved yet. But yeah, that place is addicting. Oh my goodness. I love that place. Except for when you have that one guy who can't write a problem statement. And then you just don't know what's being asked. All right, so here's the recurrence relation. All right, when n equals 0, time of 0 is just C1 because, well, you're doing a function call. And the first thing you do is if n's greater than 0, do something, otherwise you don't. So we're done. If n's greater than 0, t of n is, well, this cost, which is just equal to 2n, blah, blah, blah. We don't care. It's 2 times n minus 1 plus c. This recurrence equation for the growth rate, the Tower of Hanoi's function. If you've solved this recurrence relation using discrete structures, you'll find out very quickly that it's 2 to the n, because every n we take 2 times n minus 1 calls. This is what you need. This is the only part you need to know for this class. If you have a function, and inside of it, that function, you're basically guaranteed to make 2 different calls. Notice inside you have one call to itself, another call to itself. Where it only decrements n by 1, then you know that it's 2 to the n. If it makes 3 calls where it only decrements n by 1, then it's 3 to the n. If it makes 2 calls where it decrements n by dividing by 2, it's now linear. Hopefully you won't see that too often.
You said if it makes 2 calls and divided
Makes
by-
2 calls where it's n divided by 2,
That makes sense.
it's pretty much linear. Yeah, it's linear. All right, we're going to stop here so you have lab time to do your lab. Wow, we always run out of time. Any questions? I think it's that first day where we had so many technical problems.
Yeah, just.
That was all on your end, too.
I know, it was all my fault. Thanks for pointing that out.
Should have been prepared.
I was prepared. I guess I wasn't prepared for failure.
Exactly. It's okay, talk to us.
So it happens to all of us. Yes.
I have a GitHub question.
Okay.
I think my thing is hooked up to the wrong master. So
Okay. I'll help you with that in a moment. Any questions about the material that we went over today? All right. Let me stop this.